Alright, so we're going to get started on the Xflr5 project today. So we're going to start new, and then we are going to Necrofoils, and we are going to select 4412. That is okay. Now we're going to go to Xfoil Direct Analysis. We're going to define a batch analysis. So we have a bunch of values here. I selected them, a couple of them, like 1 e to the 6, 1.2. The highest I go to is 6 million, but the maximum it should go to, based on the Reynolds numbers we've calculated, is 4 million. And then I've set this. This is minimum, so this can be -5, and this is going to go to 20. Increments of 1. And we're doing this analysis is based off of our angle of attack. So we're going to analyze that. Alright. That's good. We have all our CL, CD, all these graphs. And you can see we start at 800. This is 80,000 for Reynolds number. We go to 6 million. So we have a good spread here. Hopefully this should be enough to get us our the amount of Reynolds numbers and simulations we need to do the wing. Alright, so then we are going to go to wing and plane design. We are going to define a new plane. Alright, we can name this plane taper, and AR aspect ratio is equal to 12. Alright, so we're going to turn off the elevator and the fin, and then we're going to define our main wing here. Color doesn't really matter, so that sets the inner and the outer airfoil, both NECA 4412. So first we're going to set our chord 2, and because this is the 0.3 taper ratio, we're going to set this to 0.6, so that gives us our taper ratio of 0.3. And then this is going to be 7.8, and that's going to give us our aspect ratio of 12. I set this offset back to 0. Looking at everything, makes sense, that looks good. So yeah, alright, so we're going to save that. Alright, that's good. We can look at our plane in here, all good. Everything in wingspan 15.6. More specifically, we're looking at aspect ratio 12, taper ratio 0.3, all makes sense. So we're going to go define an analysis. We're going to switch this to 30, and then you see our minimum, should be our minimum Reynolds number is 1.2 million, max 4 million, so we should be in good enough range. Fixed speed is going to be our polar type. And our analysis is we are going to be doing the lifting line theory, which is, I guess, wing only. So everything else we don't really need. Aero data, that's all good. Okay, so now this is -5, and that's 20, and then we're going to click Analyze, and it converged all the way to 18. That's been happening for me for my other sim, so that's all good, makes sense. Go close, and then here we can get a good look at what happens as our wing increases its angle. We can see the induced drag, the drag increases, while our lift is also increasing. So that's cool. Alright, and then we are going to go look at some of our graphs real quick. So we have all our graphs. These all make sense. So now we are going to take this and we are going to export that to CSV. These are some of the other files I've worked on and stuff like that. So I'm just going to put this video, name it that. So then we're going to go to our files here. We're going to open this. Okay, there we go. I don't know why Excel is taking so long to open. Give it a minute. I apologize. My computer is also very old, so there we go. Jeez, that took forever. Okay. Boom, let's go. Possible data loss, I do not care. Alright, we're going to take these values and we're going to put them in a different Excel that I have. Okay, so we're going to put these CL values, and we're also going to put these CD values here. Okay. So we can get rid of that. Alright, so the first thing is we want to get CLCD. So we are going to do B2 divided by C2. That'll give us that. Then we pull that all the way down. So this is our CLCD. Now we're going to start generating some of our graphs. So we're going to start out with lift coefficient versus angle of attack. So yeah, here we go. This is our first one. You see angle, and then our lift coefficient over time. Yeah, it makes sense. That's all good. Yeah. Okay, I wanted to show the last part. I wanted to show the local variation and some of our lift coefficients and such. So we can go, I believe, here. We can get a pretty good graph of what happens as we change our lift coefficients down here. So it goes boom. You can see how that slowly starts to change over time, and then that's the graph right there. And then we can go to the Excel, and I plotted all of these down in here. So we have, that's our induced drag coefficient variation for our 4 wings. This is our lift coefficient variation for our other four wings. This is our W, that's our downward velocity after the wing, and then this is the angle of attack for our wings. And that makes sense. You know, you have 12 right here, and this is for just a taper ratio of 1. So that all makes sense. Yeah, we can see here the taper ratios with 0.3, you kind of have that dip right there, but they end up having the higher angles as you go outward, and then it decreases from the span because that's the middle right there. So that's all, and that I think will be the final part. I just wanted to show the local variation of the values.